Next talk will be given by Michael Ng from the University of Hong Kong. The title is Low-Rank Tensor Completion and its application. Okay, I will make you spotlight just a moment. Oh.
I start to share already.
Yeah. Okay, I make a spotlight for you. So.
Okay.
Okay, you can start, please.
Okay. Thank you, organizer. It's nice to share some of my results related to low-rank tensor competitions. Okay. Let's start. Okay, so I think in the previous talk, roughly is introduce what are the tensor, but here we try to visualize it on the multi-dimensional arrays of tensor, like the one-dimensional, two-dimensional. So it's a matrix, and this is a vector, and three-dimensional is a cube. And in case if you want to really visualize it, we can do it in this way, like the 4D tensor. So like you have the many cubes that are along a line, and then a matrix of the 3D tensor, and even cube of the cube, something like that. So so you see that is in some way is a multi-dimensional array. There are several applications. Of course, I think I'm here is I only limited to some numerical tests or experimental results that I will present. So, but definitely that for low-rank tensor competition, that can be many possible application. One of it is about like the background and foreground separation. So in the video that you have the spatial dimensions, and then also you have a time. So because of this is like a simple cube. And of course, here is even you have the RGB or other spectral frequencies. So one of the interesting in the computer vision is try to separate the moving objects from the background. Another is very typical in image processing is to, if you have some color images, then you have some noise or some missing values, then how to recover it. So again, this is a color image. So you see that is a spatial dimension, and then you have a RGB for this. So it's a very simple third order tensor. Another one is in the hyperspectral images. I think this is one of the most important application when we talk about the low-rank tensor competition. We obtain these images or hyperspectral images from the satellite, and then to look at the Earth and about the detection of the river and minerals, mountain, etc. So again, that is can be very large data set from a third order tensor. So you see that is again you have a spatial dimension, and then you have frequencies. So so that can be very big because spatial dimension can be when the satellite cover the Earth, that can be a very large scale. So in the typical frequencies, maybe talking about 100 something, but still depends on the technology and also the satellite, the system that can be changed from time to time for different observed frequencies. Because these frequencies is also can be useful for detect a particular objects in the Earth or something like that. So here it just give you an idea. For example, why we need to do the low-rank tensor competition or the denoising or something like that. So this is one of the images obtained by the satellite. Because of some the traveling of the movement of the satellite, then somehow that will be also different sensor the problem. Then you see that we lost some of the values doing the acquisition of these hyperspectral images. So you see that in here is there will be a lot of missing value. This in a swipe form. So because of the sensor, the failure actually in the satellite. So this is one of the aim is to can we recover it or fill in some bad values based on this spatial dimension and also different frequency data. So this is somehow the output, I mean the after processing. So I think this shows one of the possibility why we need to do some denoising or even filling back the value of the low-rank tensor competition. This is another also in hyperspectral image. So you see that this is like a cloud. because of cloud. So some of the areas basically you don't have any information among here. But you see here is even though they form a strike, but because you still have some neighborhood information, so hopefully you can recover it. But here is more difficult actually. So you completely lost on a quite large region. So in this application, so how to remove the cloud in this satellite image or the remote sensing images? So you see that this is another somehow another time slot that we cover this hyperspectral image. So we make use of this time to try to help us to recover this these hyperspectral images. So this somehow we can get the results after we do this recovery. So these are many interesting applications because of the different setting or environment we need to recover. Okay, so the question is how to do this kind of the low-rank tensor competition. So of course, we mentioned that in terms of the data that can be huge, like if you have in a third order tensor, that is like the cube data, and even you go to the more high order tensor. So definitely, so many number of data points. So definitely, in order to recover properly, so you need to look for the low dimension structure in these images. It depends on what kind of images that you look like. For example, some repetitive pattern or redundant sampling like in the surveillance or in the hyperspectral images. Actually, you contains the same skin but on the different frequency bands. So this kind of you can say the redundancy information or somehow how to explore the low range structure is very important in this discovery the problem. When we talk about the low dimension structure, so one of the very classical theorem in mathematics is called the singular value decomposition. Because given the matrix, then you can decompose it into the low rank into a singular value decomposition U sigma V star. So U and V are orthogonal or unitary matrices, and the sigma is like the diagonal have a diagonal form. So so this is very nice because the U and V are somehow they are unitary or orthogonal, depends on wheel or compass. So in this case, so you can have a minimize the redundancy in the representation. But at the same time, more importantly is this sigma tells you that which are the more important in terms of the basis to describe this representation. And these called singular values, and they are from you can order it from very large to small, or even it can be zero singular value. So for example, here is a 4x3 matrices because you have 4 rows and 3 columns. So you see that at most you only have a 3 non-zero singular values. So in this cases, you can imagine this matrix is at most rank 3. Okay, so for low rank matrix, how to discover it is you can see that if we have the singular value decomposition, if some of the singular values are 0, in particular, if you have the n by n matrix, if there are only a few non-zero singular values, the other are actually they are all 0 in this diagonal form, then you know that this is actually this matrix, even though there is m by n entrances in this matrix, but this can be represented by only a few bases, and also the singular values is enough to represent the whole matrices. So this is very important because that means we only need to discover these bases, and also corresponding the weighting in the singular values is enough. So this form a very fundamental tools in the so-called low rank matrix competition problem. But of course, in our agenda is we are interested in the low rank tensor recovery. That means for given a cube or even 4D or 5D, etc. So how will you make sure of this low rank tensor recovery? How to define the low rank? And probably you see that in the like this case, like in the video, you have the spatial dimension and also time dimension, and also in the color image, say for example, you have the spatial dimension and RGB. So how to define the rank, and also is, of course, you can say that because this is a matrix, we can reorder it into the this is a tensor, we can reorder it in the matrix form or even in the vector form. So go back to this question is from here is, of course, you have a very high dimensional, very high order, the data form, but you can always reduce it by so-called unfolding back to a lower order, okay, like the one dimensional or second dimensional. But if you do this, then the question is, you will have this vectorization or materialization will probably break the inherent structure. That means, of course, originally they are labeled, then you will break it because of the reordering of the entries. Or also the time, then again, you will have the same question. So because you expect that if you keep this tensor form, then the original data that have the correlation, most likely you can make use of this information to help you to recover the whole tensor more properly. So again, the question is, we still need to answer is how to represent a so-called low dimensional structure. Okay, if you want to say, I want to, like similar to the matrix cases, I want to discover this low dimensional structure of the tensor, okay, subject to the given entries or subject to the decomposition of low rank tensor plus the small arm or whatever, or some only partial given some values. So the question is how to represent it. There, go back to the fundamental problem is how to decompose the tensor, just similar to the matrix case, how you decompose a matrix, like similar to the singular value decomposition. So in the past, many researchers has proposed different kinds of decomposition. One of the decomposition so-called is the CP decomposition, is like say for example, if you have a cube of the data, you decompose into this way. Okay, so you form the outer product of them, and then so you can see this is like the rank 1 tensor. They form the outer product of 3 vectors, and then they add up together. So this is a very natural generalization of the matrix case, because if you do not think about C1, C2 up to CR, so you have a rank 1 matrix and then add them together to form a matrix. So but here now you have a rank 1 tensor and then sum it up to form this tensor. So now the question, can we find this representation? If yes, then that can be very efficient and effective to do the recovery. But the question is, in order to find out this CP decomposition, that can be very costly, and in general that you can assume that is an NP-hard problem. So that means that it's rather difficult to do this kind of the CP decomposition. So another popular, the popular decomposition is called Tucker decomposition. Very similar to the previous case, but we try to relax it. Instead of like you forming the outer products of 3 vectors, we relax it is not necessary they are formed the relationship between the bases only exactly. We can have another core tensor to represent inside. So they still like this is like the A1, B1, C1 in the previous slide. So you have a U1 and U2 and U3, but inside here will be governed by a smaller cube. Okay, so this is like the core tensor. So in this case, we call it Tucker decomposition. The nice thing is for this Tucker decomposition, you can make use of the SVD, matrix singular value decomposition, to determine this the Tucker decomposition. That means I give you a tensor, I can write out what is the Tucker decomposition of this X by using just the matrix SVD. So is that in some sense computationally is more efficient compared with the CP. Another one is also very popular in the last few years is called the Tensor SVD. So instead of using the you can say the standard matrix vector product or the matrix to tensor product, is instead of using this kind of operation, the standard multiplication, we consider the convolution between the you can say the data. okay, to represent the tensor again. So here is you have the X, this is the third order in order to easy to visualize. So you can decompose in the U star S star V. So in this case, you will see that is like similar, very similar to the matrix SVD case, but now you have the U and V, but here there is not a standard like the matrix or tensor multiplication. We're using the convolution. Why the convolution is because they look at the line here is you have the tube of the tensor, and then now you are doing is a convolution of the tubes to define the operation. So this is why this is a convolution space, and also very similar to the matrix case, but expressed in the convolution operation. The nice thing is U and V is somehow they are like they similar to the matrix K is like the unitary and also or orthogonal, and that and here is the for S is very close to a diagonal form, but of course now is instead of the entries or a scalar you describe as a tubes. So here you see the tubes. So because of this reason, so this is very similar to our familiar matrix SVD, but the difference is now we express everything in the convolution. Or in another word, you can say that this is the X is this data original in some spatial domain or some another dimension, maybe the color or time or whatever. But now in the expressions for this tensor SVD, actually you represent it in the Fourier domain or in the convolution domain. So actually the difference is you try to build on the coupling of this data in the another domain instead of the original domain. So this is also very interesting when we discuss how this works. So I think this SVD that can be using like the decomposition. I think I skip it. So because you can use many tubes then to represent the data. So you can also define the so-called depends on how many non-zero tubes that you can define the so-called tuple rank. And also I mentioned that this is actually you represent this tensor in the Fourier domain in another way. So now you see that there can be many ways to represent the low dimensional structure of the rank, CP rank or Tucker rank or the tensor SVD. So actually in the literature there are several results to talk about is how do I guarantee to exactly recover? So based on the different sampling method and some other incoherent and other conditions in order to recover it. So for example, some even though this is an NP hard problem, but if I give you the required, this is CP rank is R, okay? It's not arbitrary, the CP rank. It say that I want the CP rank to be R, assume the underlying the CP rank is R, then what happened? What kind of requirement of the sampling size in order to recover it under this sampling method and the incoherent conditions. Or also the Tucker ranks, we can also have some other results, not on my result, of the other existing results by other papers. So they have the estimate of the sampling. That means how many number of entrances you need to take samples in the tensor in order to guarantee you can recover this low Tucker rank tensor or CP rank. So here is our somehow our result is related to this is Rn square log n square. So this is a required incoherent condition, and then this is the theorem to state that we have high probability under this sampling method we can recover the exact low rank tensor, provided that R is the rank is less than this, and the corruption rate is less than this. So I think because of time, I think, so this is, I should be control my time. So this is a phase transition, the rho and gamma depends on this observation rate, and the gamma is the corruption. So you see that this right means that you can exactly recover, but bad region means that you cannot recover. So you see that low rank is somehow requirement. And I show you some color picture of this noisy and missing values. So this is our original picture, and we have a noisy picture, and then this is our result compared with other. So you see that is here is compared with the other method, we are visually we can much better, and also you also see that in terms of the PSNR or SSIM, we are also much better result. So here is an average result of this color image database compared with the other method. Then you see that is a result in average that is much better than the other comparison. Actually, SNN is one of the you can say the main competitor using this Tucker decomposition to find out the low-rank tensor recovery. We also have some video background, so you see that this is the input image, this original, so that you can compare the visual results. So you see that our results are much better than the other method, and this is also the in terms of the accuracy, you count this foreground and background, and then actually you can see that is how good of this counting on the different the observation rate and also the accuracy result. So in general, you can ask the question is because in the Tensor SVD we need to use this matrix SVD. So in some sense, you still need to use the computer singular value decomposition. In general, it's still quite costly, especially for some problem. Of course, when you deal with very big data and whatever. So actually, in here we also demonstrate. Also, hyperspectral images is if you're using like the randomized algorithm in the projections type to find out this SVD. So you in other words is you somehow approximate the SVD, okay, by using the randomized algorithm. So what happened in terms of the result? So you see that in terms of this result, we are still quite good for some comparison, denoising result compared with other method. So, but the question is we can save up some of the time. So like here, we can save up some of the time compared with like other method, and compare with the standard BM40 the method that is quite you can say quite competitive. So we are still, of course, we are still slightly larger, but compared with you can say the original you completely use the SVD, that is a much saver in terms of the computation time. So another question is now you see that we base on the tensor decomposition, or you can say borrow the concept of the matrix K to figure out the low dimension structure. We directly measure the so-called rank of this tensor in order to recovery. So now, of course, the question is there can be many other ways to obtain the low dimension structure. So question is how or what kind of method you obtain and what is the meaning of that. So there's several methods definitely in here. I roughly mentioned that. One is you can put the rating on the tensor. This is the color image, and that's such that you can reduce the rank in some sense, or reduce all the single value somehow the overall single value decomposition. So this is another consideration. Another is you may consider other transformation, because in the standard the Tensor SVD we using the convolution. This is like using the FFT, but you can also using other transformation to help you to further to compress the tensor or the data in order to find out the rank. So this is also another interesting question. So for example, even we using a very simple wavelet, half wavelet, we can actually can better than the Fourier. Okay, so you can see that because wavelet like the half wavelet can be very localized. Actually, that can help you to localize the data into some special into some low dimension structure. So this is, I think, is useful. So here is some data you observed like the Fourier wavelet and etc. So in here actually we also develop is maybe you can find the so-called adaptively find the best representation or the basis for this kind of the image data, then in order to use it. So instead of using the standard basis like the Fourier basis, wavelet basis, you can also develop a adaptive the basis based on your image, what is the best representation, and then to try to represent it. So this is the way we consider. So visually, you can see the result are much better. So also you see that, but wavelet of course can be better than the Fourier overall. The reason is because of the singular value decomposition. You see that is because you appropriate using the transformation can help you to change the distribution of the singular value. Actually, when you use the wavelet or the adaptive basis, that can help you to further put more small singular values in your representation. So in some sense, that means you can represent your data into a more low dimensional structure. So hopefully you can recover it much better. So this is the result. So the results are similar to our previous one, but we further consider like this depends on the transformation R, so we can get this result. And actually, you can further refinement on this sampling requirement is if you make another transformation, and the sampling requirement can be further reduced to the only n log n. This is for the n if you have the n cube data. So this is the reason is because you see that in the transformation, actually, if you're using the transformation appropriately, most of them are 0. And actually, even though we have the many trips, they are non-zero, but some of the trips in the tips, some of the value are very close to 0. So actually, you can represent the low dimensional structure more in detail. Okay, so I think because I need to control my time, I think. Another way is you can use the long convex model to handle the much better in terms of the representation, or you can say the because the previous model is a convex, but here is a long convex model, so that you can represent the rank more precisely. So of course, there are many methods to construct the low rank tensor. For example, you can using the filmnet dictionary because the transformation is a unitary or orthogonal matrix. So you can using like the redundant one, like the filmnet or dictionary, to represent the data. So because they have explored the representation in a larger space, so that you expect that somehow the low rank structure can be even more well constructed. And you can also using the coupled transformation, because in the Tensor SVD, you only consider the convolution, but you can also consider like the coupled transformation. I think I skip. Yeah, here. So for example, the RGB, we can using a different filter so that you can have the transformation on the spatial domain. And then after that, you further to explore the tube on the inch filter value. So this I call it coupled transformation. So in some sense, it's also another way to further discover the low dimensional structure. So if you further to think about is, we can use like the different filter to spatial features, temporal features, spatial features to get the from the original tensor, so that you can explore to the more details in the data, and so that you can reduce the low range with respect to this new tensor. So in some sense, this is also very similar to the deep neural network when we say the data augmentation. So how to regenerate the data from your original data such that you can represent the data in much low dimensional structure. So in particular, this is also interesting because we can do it for the face recognition. Because if you have some missing data, a lot of it, but because of the different features, you can discover the human face that can help you further, not just for competition. It's also very good for the classification purpose. So here we use the Gabor transform to look for the different features. An idea, I think I will stop here very soon. So another is, well, can we using some non-local structure? That means you try to find the patch of the data and then aggregate together. So this is another way to find out the local structure. So you can go to the patch tips or even the very high dimension like the TT tensor train competition. So I think I do not. Finally, of course, you can also doing additional pair, like for example, you can put the like the non-negativity, or even here is the deep pair in to help you to further regularize. For example, that means in some sense you have another dictionary to help you to recover the images. So this can help you to get a much better result. So I think I should make a summary because almost out of the time. Yes, I try to summarize, report some of the my recent tensor competition results, mainly based on the Tensor SVD, and then also mention some of the interesting application, in particular in the hyperspectral images. I think here is the main thought is not just look at the so-called the global, the low rank like in the tensor. We can also using other method to construct the low rank structure. So that can be many different methods. I mentioned the couple transformation on also is like the multi-filters method. And another interesting issue is that can we add other constraints to help us to do this kind of the recovery process. Say, for example, most of because images or hyperspectral images, they are non-negative. So can we add the non-negativity constraint or like, for example, using other regularization like the sparse vector or even the total variation or deep pair, for example, can we have some theoretical results to guarantee similar to the low rank structure? I think these are still an open problem. So for my work, you can refer to my website and also to the DBLP. Okay, I think thank you very much.
Thank you for interesting talk. So we have many questions and 10 minutes for question. Can you find the first question from the chat window?
Let me, I try to.
The time is 9:50, maybe 8:50 for your time.
8:50 for your time. Oh, I see many questions, yeah.
First one, Cesar.
Okay. Okay, the first Cesar, yeah, I see. In your example with hyperspectral image, do you treat full image as one low rank?
No. Yeah.
Yeah, okay.
Yeah. Please read the question first.
Or it's better to split in the set of smaller image patch and combine them with. Yes, this is in my example is we treat and only one global image and then to find out. So, but of course, in maybe in some reality for very big, maybe we need to do this. I guess because I also doing this matching of the images. I think in practice, when you deal with large scale scanning on the Earth, definitely you need to combine in some way. But in any case, you still have to process the some quite large picture. They have also many different frequency bands. So I think in some sense, you still maybe we can make use of this low rank structure to help you to recover it. So the second question is about the sampling capacity of Tensor SVD is larger than CP shown in the table. Let me see. I go back to this table maybe. Let me see. Let me see. Let me see. I can share it again. That would be easier. Yeah, actually, first of all, from a different sampling method, and you can say that actually the best result for CP rank is n square or n to this cube over cube to power 3/2. And actually, what I understand is that this the current somehow the best result is this one and this one. You can argue that this is the n to power 3/2. And our case is n square log n square. So in some sense, that is talking about triple rank. But if you look at the structure on the or also the sum of the data, we find that actually you can express the low rank not just in triple rank, is in the multi rank. That means because most of the values in the trips are close to 0, so you can represent it much better. So if this is the case, then actually you reduce like the matrix case becomes an n of n square. So of course it's a theoretical, but I think in our numerical experiment, we also see that is you can see this is like the TF or different comparison of the picture on the CPU and also PSNR. We find that that is much better in terms of time and also the recovery. I think the main reason because in terms of the transformation, we can reduce this triple rank to even to a multi rank to represent the data. So this is somehow you can say the sampling refinement. Okay, another question is for large competition with like the tensor train or tensor range is often very useful to reshape the target image. Yes, exactly. There's another way, like to reshape the target image into the high order tensor to obtain a better result. But the same question is because my understanding is if you reshape it, then again, you make you will reduce the dimension. For example, for third order tensor, you have n by n by n. Then if you reduce it, will be say I don't know how many, but if you reduce it, maybe the in terms of dimension is smaller. But in terms of so-called the range structure here for each the subtensor here may be still big relatively. Okay, so I cannot say this is also another good model, but you need to balance. And another one is that we should be careful because that will be some boundary artifact. Because if you reshape it, then that will be the two neighborhood will be put in not in the exactly the same neighborhood in the train structure. So I also did some result related. Actually, if you purely on the TT train, actually that will be the some boundary the artifact will be quite serious. But of course, you can help in some other regularization or the other train. So this is still a very good approach in general. Okay, so actually go back to this point is why we do not when we do this non-local, in some sense we also do this in this way is we also actually doing this TT, but when we group them, we select them appropriately. Okay, instead of just simply rearrange all the data in the TT form. So I think this may be one way to help to resolve the problem. Okay, so why does the convolution-based is called? Oh, okay. Some call TSVD, some call tuple TSVD, but I think we call it tensor SVD because you still write the U sigma V transpose, something like that, or U sigma V star, some very similar to matrix representation. Okay, so but this is the tensor, so we say the tensor SVD. Okay, but to me, I think somehow when you in particular using a different transformation, we even call it transformed tensor SVD or something. Yeah. Yes, tensor SVD can be extended to a high order tensor, but but the question is you will have a lot of transformation to be considered. So but luckily for really large order, the tensor is up to like the time and frequency, maybe 4 or even 5. So still reasonable. So you will using instead of just one-dimensional Fourier transform or one-dimensional unitary matrix, you may consider the tensor product of the unitary matrices, something like that. So the exact Tucker decomposition can be computed efficiently, but it's not unique. Well, the exact is hard to compute. What about the tensor? Oh, this will be exact. It's a unique decomposition for tensor SVD. So this is also why good. I should say that the Tucker decomposition is also exact. But if you want to say, given a tensor, I want to find the Tucker range is R1, R2, R3, find the optimal the Tucker decomposition with this range, that would be very difficult. I mean, still an open problem to find an efficient algorithm. But if you say, I give you a tensor, I just want to find out what is the Tucker decomposition, that can be exact because you're just using a matrix SVD. In the tensor SVD, how to empirically choose the mode? Oh, this is another, I do not explore here, but in some sense, I also answer. In the images, like hyperspectral images, we usually choosing the frequency band or the video, we choosing the time to represent the tube because that can be, because the space, in some sense, the spatial dimension you can handle by the SVD. So we're using this like in the signal processing to compress or redistribute the frequency mode or also the time mode in the representation. So, but this is still an interesting problem. Can you choose another? Yes. So this is why another idea I mentioned it briefly is why we consider coupled transform. So because we deal with the images, we have the the spatial dimension and also another dimension, maybe time or frequency. So we consider other filter to apply to the spatial dimension because they are two-dimensional, and also apply the other transformation on the frequency or also the time. So this is a usual the trick. This is also why we consider multi-scale filter and the other. Can you say more about how you actively learn the basis from Tensor? How is the, actually, this is more computational. That means in the representation on this transformation, instead of using the fixed basis, we tried unfolding all the troops into a very, you can say, thin matrix. Then you have many columns. We just find out the SVD on this matrix so that you can get the representation of the U on these columns, and just pick up this U to put in the basis. Of course, at the beginning, at the first run, you don't have any, you have a missing value. You cannot find out what is the best representation. So we need to go through the optimization process. Maybe we have some initial guess, or by other method, standard basis, we get some reasonable picture, and then now I can find out what is the best U to use it. So this is the basic idea. Okay. So I think that's all, Siobhan. I mainly try to answer all the questions. Hopefully it's all right.
Mm.
Okay, thank you.
Okay, thank you for your great talk. Thanks again.
Thank you. Okay, thank you.